Hi everyone, my name is Xusheng Luo. The title of my presentation is Socially Aware Robot Planning via Bandit Human Feedback. My collaborators are Yan and Professor Zolanos. Socially aware robot planning considers the problem of planning socially aware trajectories for robots operating in environments that are populated by humans. A robot trajectory is socially aware if it doesn't interfere with humans in any way that causes discomfort. Consider the scenario where the robot is required to navigate from its initial location to target location. Humans may have individual feedback on the planned trajectory. Some may complain that the robot is too close to them. Some may complain the robot interferes their sight. And others may complain the robot affects their remote work. We capture such feedback using the Bandit feedback, which indicates a complaint or no complaint on the part of the robot trajectory that falls in human vicinity. Note that such feedback doesn't reveal any contextual information on the locations of the humans or the reason for complaints. In this way, given a trajectory, we assign a social value as the number of complaints it incurs. In this example we give, the social value is 3. Our goal is to design a trajectory that achieves the 0 social value while reaching their target location. Developing planning methods that can incorporate such unknown and high-level feedback is necessary to have robots that can efficiently coexist with humans. Since humans can move in obstacle-free space, their feedback mechanism may also change accordingly. Therefore, some people may complain about the socially aware trajectory due to their new locations or their new feedback mechanism. So, the socially aware trajectory planned for the previous period of time might not apply for the future period of time. Hence, we should be able to recompute the socially aware trajectory in a fast and online manner. What distinguishes our work from the existing ones is the introduction of the human feedback that are unknown and cannot be easily described mathematically. To the best of our knowledge, this is a new framework for socially aware robot planning that is not restricted to avoiding collisions with humans, but instead focuses on increasing the social value of the robot trajectories using only Bandit human feedback. In the related work on socially aware robot navigation, they mostly focus on human-robot collision avoidance, while the human feedback can capture more general requirements. The field of trajectory optimization often requires the objectives to be known and mathematically expressed, which is not the case in our work. The most relevant to the method proposed here is the recent work on learning-based trajectory optimization using human preferences. They can only be applied to stationary problems where the utilities of humans do not change over time. This is because a learned policy for one preference model cannot be easily adapted to another preference model corresponding to different human utilities. However, even in the stationary case, the amount of data required by learning-based methods is typically very large. This means humans would need to be queried for feedback a prohibitively large number of times, which is undesirable. Before we provide the problem formulation, we first present two aspects. The first aspect is about the human motion. We consider that humans are distributed possibly in a spatially uneven way in the environment. Also, we assume that the model of human dynamics is unknown, making it unlikely to predict the moving pattern. Consider a sequence of k plus 1 time instants. We make the following assumption on the motion pattern of the humans. First, every time interval is larger than a constant. Second, humans move instantaneously between the current and next locations, and they remain stationary during the time interval. Compared to the existing works where humans move frequently, we capture the situation where human motion is infrequent and sporadic. For example, it models typical work environments where humans remain around certain locations for a while and then quickly move to other locations to perform subsequent tasks. The second aspect is about the human utility. Recall that everyone has the individual feedback, and this feedback also varies over time. We model the human feedback using an implicit human and time-dependent utility function H, which indicates the preference of individual key regarding the discrete trajectory x at the ith time instant. Particularly, the utility function returns 1 if individual key calmly spot the trajectory. Otherwise, it returns 0. We make the following assumptions on the feedback provided by the humans. First, human feedback is bandit and which is unknown, can't be mathematically described. Second, the human utility function doesn't change during the time interval, but it can change at time instants when humans move. After defining the human utility function, we capture the social value of the trajectory during a time interval by the total number of complaints incurred by that trajectory. Then we call trajectory socially aware if it incurs 0 complaints. After introducing the human motion and human utility, given a sequence of k time instants, our goal is to design a sequence of k clean, free, dynamically feasible, and socially aware discrete trajectories, one such trajectory per time interval. We call the trajectory clean free if it never collides with any obstacle, and dynamically feasible if it respects the dynamical constraints. These two will serve as a constraint in the optimization problem, and we aim to minimize the cumulative social value over key trajectories. Note that this optimization is an offline optimization problem, and it can be solved after the last time instant, assuming that all utility functions h are known in hindsight. However, if the human utilities are unknown and a new socially aware trajectory has to be designed during every time interval, the original problem needs to be solved in an online fashion. We can do this by solving the optimization problem during every time interval, which minimizes the human utility within the single time interval. Finally, the socially aware robot planning problem considered in this paper can be formulated as follows. Given a pair of start and target locations and a sequence of discrete time instants, design a sequence of clean free, dynamically feasible, and socially aware trajectories, each of which solves the optimization problem 1. Note that the objectives in the optimization problem 1 are time varying due to the varying human locations and feedback. Before introducing the optimization method, we reformulate the online problem 1 by manipulating the constraint set and then develop a novel method that combines zeroth order optimization with model predictive control to solve the online socially aware robot planning. Specifically, we define F to be the set of clean, free, and dynamic feasible trajectories that are in the neighborhood of the given trajectory x, and we define the new problem as 2. Note that problems 1 and 2 are equivalent. To say this, observe that if x star is the optimal solution of 1, then it's clean, free, and dynamically feasible. Therefore, it belongs to the set F. Since 1 and 2 share the same cost function, this means that x star is also the optimal solution of 2. On the other hand, if x star is optimal solution of 2, then it's clean, free, and dynamically feasible. Therefore, it satisfies the constraints of problem 1, which means that x star is also the optimal solution of 1. However, computing the F, the set of clean, free, and dynamic feasible trajectories that are in the neighborhood of the given trajectory, is generally difficult. Instead, we can compute a single trajectory that belongs to this set using off-the-shelf motion planner. Let M denote such a trajectory generated by motion planner, and we reformulate the problem 2 as problem 3. A sufficient condition for the feasibility of problem 2 is that problem 3 is feasible, since the trajectory output by a motion planner belongs to the set F, the set of clean free and dynamically feasible trajectories that are in the neighborhood of a trajectory. However, it's difficult to satisfy the constraint 3 using a motion planner without any notion of feedback. That is why we obtain the penalty-based reformulation of 3, which is shown in 4, where ρ is a positive penalty parameter and the knob of difference measures the tracking error between the given trajectory and that generated by the motion planner. In this way, the motion planner provides a target trajectory that its optimization algorithm tries to track. So there is a notion of feedback between the motion planner and the iterative optimization process. Note also in 4, the trajectory X may not be clean-free or dynamically feasible, and it's not meaningful to request human feedback on an infeasible trajectory. That is why we replace X with MX in the human utility. That is, we query humans for feedback on the trajectory output by the motion planner rather than the trajectory X. After obtaining the unconstrained optimization problem 4, we use the zeroth order method to solve it. The zeroth order method is a derivative-free optimization framework that optimizes an objective function based only on the function evaluations, which makes it ideal for our case, since the utility function in the objective is unknown. The gradient estimation of the human utility at the current iterate is shown below. We drop the subscript I for simplicity, where n sub x is size of a discrete trajectory, and the vector u is a random vector sampled from a uniform distribution in a unit sphere. We perturb the current iterate by a small amount delta in both directions of the unit vector u, and then query human feedback on these two perturbed trajectories. We refer to the gradient estimation here as a full perturbation scheme because it perturbs a whole trajectory. The main limitation of zeroth order methods in general is that their convergence is slow, especially when the problem dimension is high. This is the case here, as the number of waypoints in the trajectory x can be very large. To address this limitation, we propose a local updates of the trajectory, restricted to those waypoints that are directly affected by human complaints. This is a reasonable assumption, since humans are more likely to complain on the part of the trajectory that causes them discomfort, rather than on the whole robot trajectory, which may not even be fully observable. We go back to the motivation example at the beginning. These red waypoints inside the ellipses are these that incurs human complaints. We only perturb this subset of waypoints, and we refer this as a local perturbation scheme. To develop the proposed local update scheme, we define the index set S that captures the local awareness of human key, that is, those waypoints in the whole trajectory that directly affect human key at the time instant. Then we get the whole subset of complained waypoints of the whole group of humans. Next, we perturb the trajectory locally, where u sub s is computed by setting the entries of a unit vector u that are not in the set S to be 0. And last, the modified zeroth order gradient estimation is shown at the bottom, where W is the dimensionality of the single waypoint. Since the size of the complaint waypoints is smaller than the whole trajectory, the convergence speed of the zeroth order method can be greatly improved. To solve the problem 4, the zeroth order method alternates between two steps. The first step computes the total gradient, either through full perturbation scheme or local perturbation scheme. This total gradient is the sum of the gradient of the human utility and the gradient of the tracking error. After obtaining the estimated gradient, the next iterate is updated in a usual way. Note that up to now we only solved the optimization problem at the one-time instant. Next, we show the integrated online socially aware planning algorithm during the whole time period. This algorithm consists of two layers of iteration. The outer iteration is for a sequence of k-time instants. The inner iteration is to solve the optimization problem at each time instant using the zeroth order method, which is said to implement gradient update up to n times. In the common online algorithm, n equals 1. Within the inner iteration, the humans are queried for feedback twice, one for the two perturbed trajectories and one for the evaluation of the updated trajectory. Therefore, the number of queries during each time interval is twice as much as the number of inner iterations. The inner iteration terminates if the trajectory output by the motion planner has zero complaints or a predefined maximum number of iterations is reached. Then the algorithm returns the trajectory returned by motion planner as a solution. At the next time instant, the human in the environment may move and their feedback mechanism may change. The trajectory from the previous instant is used as a warm start to initialize at the next instant. Finally, we present multiple case studies that illustrate the efficiency of the proposed algorithm. We consider a square continuous environment of size 20 by 20, where two square obstacles of size 2 by 2 are located near the center. Starting location of the robot is at 0, 0, and the target location is at 20, 20. We consider a unicycle robot model and use a model predictive controller (MPC) as a motion planner in the zeroth order method. We first generate a trajectory that consists of 15 waypoints that connects the initial and target location. This trajectory can be any arbitrary trajectory. See the red arrowed path in the figure. This trajectory constitutes the initial trajectory for the proposed zeroth order method at the time instant 0. Furthermore, we consider a group of humans in the environment, which varies from 20 to 60. At the initial time, we assume that the human population is randomly located in the environment, shown as the blue dots in the figure. To quantify human feedback, we assume that each individual possesses a restricted zone and makes a complaint if there exists a trajectory segment passing through the restricted zone. The restricted zone is represented as a red circle in the figure. The radius of the circle is human-dependent, and it reflects the sensitivity of an individual to the violation of their restricted zone. For every human key, we randomly take the value of the radius in the set from 0.3 to 0.7. Then at subsequent time instants, each individual moves by uniformly sampling a location within a circle of radius centered at their current location. The radius takes values among 0.3, 0.5, and 1. The size of the circle captures the range of individuals' movements. Furthermore, the radius of the restricted zone is randomly updated at subsequent time instants as well, which captures the temporal variation of humans' feedback. In the first case study, we compare the full perturbation and local perturbation schemes in situations where humans do not move. To this end, we set the number of outer iterations as 1 and the number of inner iterations as 50. The number of humans varies from 20 to 60. For a specific value, we report the mean and standard deviation of the number of iterations taken to find a clean-free, dynamically feasible, and socially aware trajectory, averaged over 20 trials. We also present trajectory length as another metric to compare the full and local perturbation schemes. Observe that for each scheme, both the average number of iterations required to obtain a socially aware trajectory and the trajectory length grow as human increases. In comparison, the local perturbation scheme requires fewer iterations and generates shorter length trajectories than the full perturbation method. In this slide, we show one sample trajectory returned by the local perturbation scheme when the number of humans is 60. We see that the trajectory returned by MPC motion planner successfully avoids human restricted zone and obstacles, whereas its reference trajectory returned by the zeroth order method violates the restricted zone and collides with obstacles. In the second case study, we consider situations where humans move and their corresponding utilities change over a period of time. Therefore, we solve an online optimization problem. We measure the quality of the sequence of trajectory returned by the solution of online problem using the cumulative regret, which is the sum of social value over the time period from the beginning up to now. In the following simulation, we consider a sequence of 30 time instants, fix the number of humans at 50, and vary the human radius among 0.3, 0.5, and 1, and also the maximum number gradient updates from 1 to 4. That is, we only perform a handful of gradient updates within the inner iteration, which eases the burden on human for feedback. The value of the movement radius affects the relative change between human distributions, and therefore the relative change between optimization problems at consecutive time intervals. For each combination of movement radius r and the maximum number of gradient updates n, we run 5 trials that report the mean cumulative regret as a function of the time instants. At each time, the full and local perturbation schemes are used for the same human distribution and human utility function. We depict the growth of the cumulative regret with respect to the maximum number of iterations for different human motion radii. In each figure, the black solid line is the baseline, which is the mean cumulative regret incurred by initial trajectory returned by MPC. This baseline is equivalent to the case where n equals 0. Furthermore, lines of the same color represent one case of maximum number of iterations. The colored solid lines represent the cumulative regret achieved by the local perturbation scheme, and the colored dashed lines for the full perturbation scheme. Observe that, compared to the baseline trajectory, the full and local perturbation schemes can improve the social value of the trajectory with few queries, particularly using only 3 iterations at each time instant as shown in the blue line. Both methods can provide a good trade-off between decreasing the cumulative regret and limiting the human query frequency. Observe that in the first figure for movement radius 0.3, the local perturbation scheme performs better than the full perturbation scheme for all values of n, but this advantage becomes weak as the human motion radius increases. This is because as movement radius grows, the relative change in the human distribution becomes large, and so does the relative change between consecutive optimization problems. In the local perturbation scheme, for each optimization problem, more waypoints of the trajectory returned from the previous time instant has to be modified due to the larger change in the human distribution when movement radius increases. To sum up, we consider the problem of designing clean, free, dynamic, feasible, and socially aware trajectory for robots operating in environments that are populated by humans. We formulate the planning problem as an online optimization problem that minimizes the social value of the time-varying robot trajectory. We employed zeroth order optimization methods to solve this problem, which we combine with off-the-shelf motion planner. To the best of knowledge, this is the first approach to socially aware robot planning that is not restricted to avoid collisions with humans, but instead focusing on increasing the social value of the robot trajectories. Thank you for your attention.